Hi, good morning. I hope you are doing good. Today I'm not going to teach you what is machine learning because for that you can follow the Andrew Ng Coursera course, which is based on machine learning specialization. He defines all the mathematical equations behind the machine learning models. Rather, we'll be doing a real project on QSAR data, quantitative structure activity relationship, where you can download the structure from Zinc database or CHEMBL database, and you get the molecular structures out of that, you get the smiles out of that, and then you can process the data, you can feed into the machine learning models, not only the normal machine learning models like SVM or random forest or linear regression, something like that, but also we are going to do the deep learning models. For the deep learning models or the neural networks, you require the NVIDIA GPUs, but for the normal models, laptop is more than enough to perform the machine learning calculations. I personally did almost like 230 million compounds, and I fed all the structures into my machine learning model, and it predicts really well. If your data set is very good enough to process all these kinds of data, then that would be fantastic. So in this tutorial, I'm going to process a data of around 27,000 SMILE structures or zinc structures with the molecular properties like molecular weight, polar surface area, hydrogen bond acceptors and donors, and we'll be predicting the LogP as well. So in a moment I will show you from the scratch how you can perform machine learning on your QSAR data to predict the properties. See you there. So the first thing is to create a folder called QSAR data, and then you provide your data set. I will show you in a moment how my data set looks like. And this is the requirement.txt file I will upload to my GitHub channel. I will provide the link in my description. Okay. And you navigate to a terminal. So I'm using warp in this. And I mentioned in my previous video that you can install or create an environment using the UV package management because it is much more faster. So the command is UV venv and whatever the environment name that you want to give. Okay, now it's created. Then you activate that. Okay, and I'm going to show you the requirement.txt file because it contains some of the NVIDIA libraries. Those who have GPU, they can install the NVIDIA libraries like TensorFlow and also some of the libraries that are meant only for the GPU purposes. Okay, and those who are running the normal models, they can use the CPU version of the Torch like PyTorch, the CPU version. Okay. So for instance, if you want to install a package called matplotlib and look at how fast it is, the UV pip install matplotlib, you can see that if you try to install using the pip package, it might take time, but the UV can do it faster. Similar way, pandas, polars, plotly, and you can feed all the commands at a time. So I'm going to say notebook, or maybe some of the other packages like TQDM. This is for the progressing bar. Okay, and you can see it can install all the packages. Now the agent mode has been activated. This is the beauty of the warp terminal, that the agent mode can be activated when you simply feed a command to that, and it can also perform the same thing with your normal command as well. And now you can see that all the packages have been installed. I have already performed the machine learning model because it will take some time, and I'm demonstrating on my laptop. I'm not using my CPU, but I will show you. And the best thing that you can do is since I provide this requirements.txt file, you can directly install UV pip install -r requirements.txt. It will install all the packages that you require. Okay, so on my laptop it will not run because it requires the GPU and stuff, but if you have NVIDIA GPUs and if you want to install TensorFlow GPU version, then you can utilize your PC to install all the libraries. So I'll provide the requirements.txt file. Okay, let's navigate. Now this is done. Let's navigate to the notebook that I prepared, and I'm going to show you one by one how you can process the data. And before that, let me show you how my dataset looks like. This is 27,000 compounds downloaded from a Zinc database, and I predicted the properties by using Discovery Studio and Schrodinger. Both of them I have used. So let me just make it bigger, and you can see that. So the first column is the name, the Zinc IDs. These are the canonical smarts, LogP, whether it is chiral or not. Okay, and the next thing is about the log-D, molecular weight, aromatic rings, hydrogen acceptors, hydrogen donors, how many number of rings, the molecular polar surface area, this is the chiral flag, whether it is chiral compound or not, and the pK values. But we are going to focus on LogP, and then the molecular weight, acceptors, donors, and molecular surface area, because these are the properties that we want to predict when we feed the data into the machine learning models. So I'll show you the code, how it works, but this is the data that we are going to process in this tutorial. Okay, so it contains almost 27,000 compounds. Yeah, 27,178 compounds. Okay, this is the main data set that we are going to feed. I have this notebook file which I'm going to open by using Jupyter Notebook. I type in the command and it will open a browser with all my files listed over here, and then if you click here, it will open up the Python notebook, where I did run all the machine learning model. Okay, so I provided the requirements.txt file so you can install directly, even on the notebook as well. If you have NVIDIA CUDA libraries and TensorFlow you want to install using the GPU version of that, you can install by using this command. I provided all of them in the requirements.txt, and these are mostly the requirements.txt file, as you can see. Okay, let me also open up the file which I have already performed. As you can see here, let me just make it bigger so that you can see. So once you install all the libraries, then you navigate to the second step, which is preparing your dataset. So first thing first, you have to import the library, which is the pandas version. Now let me just make it bigger so that you can see. Okay, so first thing, you have to import the pandas libraries. Okay, and then you provide the dataset path, which is the 27k dataset.csv. This is my dataset. You need to provide the exact name with the inverted commas. Okay, then if this is the command where you can load the dataset, and if the file name mismatches or your file is not found, it can tell you that it cannot load your dataset. Please check the dataset path. You can provide the path as well. Okay, and then this is the very basic command where you can identify the shape of the dataset, how big is your dataset, and you can also provide how many columns are there in your datasets. So let me show you the outputs from those particular commands. So now you can see it found the dataset and it's loading my dataset into the notebook, and then it contains 27,177 molecules. I have shown that 27,178 because the first row is the header, right? So pandas consider the CSV file with the header file, and then consider all the other as the data. And since I mentioned the datasheet shape, it looks like this. So 27,177 rows with 14 columns, and the column names are name, canonical, smile, smarts. I've shown that. So if you count these headers, it will be a sum of 14. So 14 headers. So this is how you can predict the dataset shape. And then next, we need to clean up some of the column names, because sometimes you want, and these names are too big. So in this case, as you can see, my second column is canonical smile. So I need to convert into, suppose I want to convert into smiles only. Then you can use this particular command to convert canonical smiles into smiles. And you want to convert the name, the first column, which is the name, into zinc ID. So you can convert that as a zinc ID. Okay, the name into the zinc ID. So I'm using the Schrodinger descriptors and also the Discovery Studio descriptors instead of recalculating with the RDKit. But if you want to follow the how to calculate the molecular descriptors using RDKit, you can follow this particular video where I mentioned that how to calculate all the properties using RDKit.
Go into the
Okay, that is going on, but this is the video that you can follow in my channel to calculate the properties. Okay. The next thing is renaming the columns. So these names, the molecular weight, molecular polar surface area, these are too big names. So I want to convert into something smaller. So I converted them into molecular weight, TPSA, HBD, and HBA. And these are my target columns. I mean, these are the properties that I'm going to predict if I feed a new molecule into my machine learning model. So these are basically the target columns. And all the other things that you have seen, those are the features, the smiles, the zinc IDs, etc. They are the features, but these are my target columns. So in machine learning models, there are two things that you need to consider. How many features that you are going to train in order to predict the target properties. So these are the target properties. So preparing molecular properties from the Schrodinger dataset using 5 molecular properties from the Schrodinger descriptors. Those are my targets. And cleaning the dataset. As you can see, dataset size was 27,177, but now it is 26,887. 98.9% has been written, and some of them, which has maybe some of the duplicate smiles, it has been removed. And this is the sample of the dataset, how it looks. So after the rename, it looks like I have converted the name into zinc IDs. These are the smiles, canonical smiles into smiles, molecular weight into MolWt, molecular polar surface area into TPSA, LogP, hydrogen bond donors and hydrogen bond acceptors. And these are the target property statistics, because these are my targets. So some of the statistics, that how many counts are there, what is the mean molecular weight, mean polar surface area, LogP, hydrogen bond donors, hydrogen bond acceptors, etc. And then I save that particular dataset into a file name called clean molecular dataset.csv. So here. So this is the command to save the dataset. So let me show you the clean dataset that I have saved. So it will be over here. Yeah. So this is the dataset that has been saved after renaming, cleaning all the duplicate smiles, etc. So now you can see this is the perfect clean dataset that can be fed into the machine learning calculations. Okay, so this is basically the data processing of your dataset. This is really important. If you miss this particular processing strategy, then your training model might not be that good. So you have to be carefully perform the dataset itself, the data processing of your dataset, and then you can perform all the machine learning models. So next we move on to step 3, which is the data analysis with the interactive plots. You can create beautiful interactive visualization to understand your data. You don't need to navigate to your data set every time, open it in Excel, and then you want to see how many how my data looks like. So rather you prepare these visualization plots using the Plotly library, and then you can visualize all your distribution of molecular weight, TPSA, hydrogen bond acceptors, donors, and LogP values. Okay, and this is the code that you can feed into your notebook, and then you can see different types of visualization plots. One is the distribution of the molecular properties, as you can see here, how well your molecular weight has been distributed on your data set. This is your polar surface area, LogP, hydrogen bond distribution, and hydrogen bond acceptors, hydrogen bond donors and acceptors. And you can prepare a correlation matrix as well between the properties, how well it is correlating with your data set. And then you can also visualize some of the interactive plots using the Plotly library. And this is your summary statistics, that how many molecules that you have, what is the average molecular weight, which is around 189 daltons. This is your polar surface area, which is around 44.5, LogP 1.44, hydrogen bond donors 1.1, hydrogen bond acceptors 1.5. This is only to visualize the data. It's nothing to do with the machine learning models or something. So it's just to understand your data, how well your data has been distributed. This is also a very important strategy to look how your data looks like, rather than visiting all the time to the Excel file to see how the data looks like. Because if you have like millions of data, then it might be not possible to open it in Excel file. So you rather prepare these plots to visualize your data. So after visualizing the data, the next thing that we are going to do is convert the smiles into fingerprints. And these fingerprints are nothing but the molecular patterns. So I'll give you an example that if you have a shopping list and you go to a grocery store and ask the shopkeeper to look into their databases, suppose if they have bananas or not. So he will quickly look into he will quickly type in the product number of the banana, and it will tell you that yes or no, I do have bananas, or I don't have any bananas. So it will give you answer. The shopkeeper will give you answer like yes or no. Do you have oranges? Do you have grapes? So similarly, he will look into different types of product numbers, and then it will tell you yes or no. In a similar way, the computer cannot understand the human language, which is yes or no. So it has to convert the yes into 1 and no into 0. And the product numbers are nothing but your molecular patterns. So smiles have these molecular patterns like C, C, N, O, something like that. So in our calculations, we are using 2048 Morgan fingerprints. So these are the fingerprints which contains all these molecular patterns. For instance, if you take a benzene ring, it has an aromatic ring. So each of the molecular patterns like aromatic ring, carbon, nitrogen, oxygen, CC bond, ester bond, these are nothing but your bits. So computer assigns all these molecular patterns a specific type of bit number, or from the example, it's the product number, right? So computer will quickly, so when you feed one smile into the machine learning model, it will quickly look into the database of the molecular patterns, and it will quickly look whether the benzene ring has nitrogen. Then it will assign, no, it doesn't have any nitrogen, so it will assign 0 to it. It has aromatic ring, yes, so it will assign 1. It has CC bond, yes, it has. Does it have carboxylic acid group? No, though then it will assign 0 to it. So 1 and 0 is based on the molecular patterns that you have in your database, and those molecular patterns are nothing but your bits. So bit 1 is assigned to aromatic ring, bit 2 might be assigned to the carbon, bit 3 might be assigned to carboxylic acid, something like that. So we have altogether 2048 molecular patterns. So whenever you feed one smile to it, it will look into the database, look for the bits, and then it will assign 1 and a 0. So I'll also demonstrate the same example in our code, and I will also tell you how these fingerprints work. So this is the code. We are using the RDKit library, and we are using the Morgan generator to generate the fingerprints out of the dataset that we are going to use. So we are using 2048 number of features or the bits, okay? And how far we are going to look? We are going to look around a radius of 2 angstrom, okay? And once you write this code, it will give you, so you need to convert the molecular fingerprints from the smiles, okay? The smiles that you fed from your database, it will quickly look into the whole smile structures in your 27,000 rows, and it will try to create all the fingerprints. And you can see that you have 26,887 rows with 2048 bit patterns. And the target matrix shape that you have, these 5 properties that you are going to predict, they are considering all the rows with the 5 target properties. And once it converts all the smiles into fingerprints, it will save it as a molecular fingerprints.npz file, okay? And this is how you convert your smiles into fingerprints. Let me also tell you that how your fingerprints bits converts to molecular weight, or maybe to LogP. You know, in a similar way, you can convert all of them into all the properties, all the target properties. So as I mentioned, fingerprint bit represents whether it has a presence of 1 or absence of 0. So for instance, you take an example of CH4. The molecular weight is 16.04 daltons, right? So CH4 has carbon atom. Yes, it will assign 1 to it. Does it have an aromatic ring? It will assign a 0. And these are the bit numbers. This is for example only. So for instance, bit 0 has been assigned to carbon atom. So it will look quickly into the 2048 molecular patterns, and then it will look for the carbon atom. Does it have a presence? Yes, it will convert into 1. It will assign 1 to it. Does it have a aromatic ring, which is the bit number 1? It will tell you no, it doesn't have a aromatic ring. And the next thing that it will ask you that does it have a CH bond? Then it will assign 1 to it. Does it have a CC bond? It will assign a 0. In the case of benzene, does it have a CC bond? As you can see, it has assigned a 1 to it because it has. So it looks into all the 2048 bit patterns, and it will assign 1 and 0 to it, okay? And these are some of the models that we are going to feed into our machine learning model, and how the model predicts it. So in a linear model calculations, you can see that 78.1 is nothing but, for instance, we are looking into this aspirin structure, right? So aromatic ring has a molecular weight of 78.1 daltons, right? So it will quickly look into the database. So for instance, the bit 123 represents your aromatic ring. So it will assign 1 because it has an aromatic ring. So it will say 1, the presence of aromatic ring, into the molecular weight of that particular aromatic ring, which is 78.1. Next thing, it will look into carboxylic acid. Does it have a carboxylic acid? It will say yes, it has a carboxylic acid. So it will assign 1 to it, and 1 into your molecular weight of the carboxylic acid. So in this way, it will calculate, it will sum up all the presence of those molecular bits into the molecular weights of that individual patterns, and then it will finally sum it up to give you an estimate of that molecular weight. Okay, so this is how this is just an example, how the linear model works. And the final predictions will be linear regression will give you 182 daltons, random forest will give you 179, neural network will give you 181, and you can see that actual molecular weight is 180. So this is how the computer can understand all your SMILE structures, whatever the CSV file that you provide. It will understand the molecular bit patterns, and then it will convert into specific molecular patterns, and then it will calculate the specific property that you might want to explore. Okay, so for instance, take this one. So we have two different types of fingerprint patterns. So number one is the max key, which has only 166 maximum fingerprints, but Morgan generator has 2048 patterns. That's the highest number that has been provided by RDKit library. So for instance, this is the max key, which has the bit number 1 assigned to isotope, bit number 2 assigned to the elements between 103 to 256 atomic numbers. These are the very heavy atoms. Bit 3 is for these elements, etc. Right? In the Morgan fingerprint, you have like 2048, and you can see that all of these bits have been assigned to a specific molecular pattern, and the computer will quickly look into, or your machine learning model will quickly look into the database of 2048 molecular or Morgan fingerprint, and then it will assign 1 and 0, and finally it will calculate all the properties that you are targeting for your machine learning model. So this is how the fingerprint works. Okay, so that's why it is very crucial to convert your SMILEs into fingerprints, and this is the code that will convert all your fingerprints into, or all your SMILEs into fingerprints. So the feature matrix size or the shape is around your rows, that is 26,887 with 2048 fingerprints, and this is the matrix shape, that is your rows into 5 target columns that you want to predict all the properties using the machine learning model. Okay, and finally it will save all the fingerprints to a file called molecularfingerprints.npc, and this particular molecular fingerprints.npc file you can feed into the next, which is the machine learning models that we are going to use. Now we move on to the multi-target molecular property prediction with the advanced models, which are the machine learning models. So we are using the scikit-learn library for the test and train dataset split, and also we are using random forest, gradient boosting, extra trees, linear regression, ridge, lasso, ElasticNet, k-neighbors, and decision trees. So these are the normal machine learning models that people use in every data sets. Okay, the latest or the advanced models that we are going to use is the CatBoost model. I'm going to explain you what CatBoost model is, and also we are using some of the deep learning models as well. So these are the linear models. Fast, they are very fast, you can run it on your CPU, but there are some of the deep learning models that you require GPU for that. So let me just explain you one by one, that once you perform the split between the training dataset and the test dataset out of your 26,887 rows, you are going to feed them into different types of machine learning models. So first one is linear regression, second one is the ridge regression, third one is lasso, and fourth one is ElasticNet. And these are the tree based models that you are going to feed, which is the random forest, extra trees, decision trees, and also these are some of the gradient boosting models, which is the gradient boosting and XGBoost. These are some of the simpler models, LightGBM, etc. And this is based on the k nearest neighbor method, and also these are some of the basic machine learning models. But when it comes to the neural network, you are going to use the multi-layer perceptron model, and this is an advanced model which is called CatBoost model, and you are going to compare all the models to identify which has the best value for the predictions. Okay, and these are some of the fast advanced models, but it requires GPU for your calculations, which is the fast neural network, which is the AdaBoost, bagging ensemble, and fast voting ensemble. And also we are going to use some of the TabNet models. So these models you might have encountered in some datasets, but in QSAR I have not seen these models whether they have been applied or not. But I have been applying all these models to my calculations, and it really performs well for my datasets. There is also a model called TabNet, and all these models that you are going to feed into, it will give you a quick, nice summary of your R-square value, the RMSE, whether it is overfitting or not. So it will give you the whole landscape of the ML models that you can use. So let me also tell you what are these models. So first thing first, what we are going to do is we are giving the fingerprints that we converted from the smiles as an input data, and we have almost like 13 plus algorithms, and we are predicting 5 properties, that is molecular weight, hydrogen bond donors, acceptors, LogP, and the polar surface area. Okay, and I have explained you how the molecular fingerprints work from your smiles. Okay, and these are the target properties we are going to predict, and we are going to split the data into 80% training and 20% testing. That's what many people do, and this is what I have done as well. So out of 26,000, you can see that 80% of the data, that is around 21,509 molecules, has been fed for the training data set, and the test set size is 5,378, which is around 20% of my data. How many features that we are going to use? Number of molecular features are 2048, and these are the target properties to predict, which is molecular weight and LogP, etc. We are using 5 optimized fast models. Previously I have also used some of the slow models, but it was not performing well. For instance, these models have been removed. These models have been performing really slow for my datasets. If your dataset is more than 10,000 rows, then it might not perform so fast. So I have only utilized the fast models, which you can run using the CPU, and if you have GPU, then you can run all your neural network or the deep learning models. Okay, so we have like 18 different models on 5 properties. So I'm using 18 different types of machine learning models to predict the 5 properties. Okay, so so what we are predicting is RMSE, R-square matrix, to identify how well the data has been performed. And these are some of the models, like linear models, and you can see the input is your molecular fingerprints, and the linear regression will work like each of the fingerprints it takes into account, and then it will identify all the patterns and then sum it up. Ridge, Lasso, and ElasticNet also follow the same pattern. These are the linear models. So they try to find out the linear relationship between the molecular features and the properties that we are going to predict, and each fingerprint bit gets weight. So these are nothing but your weights. Okay, and these are very fast. And if you want to dive into what are these linear models, how the mathematical stuff behind this, you can follow the Andrew Ng course. He explains really well how these weights have been assigned to these linear models. Okay, next we have these tree-based models, which is the random forest, gradient boosting, etc. So what it does is create a decision rules based on the fingerprint bits. If a molecule has aromatic ring or carboxylic acid or CC bond, then it will assign a LogP value of 2.3. Okay, so it has a decision tree based on the fingerprints only. So that's why these bits are really important for any sort of models, whether it may be linear, neural network, or tree-based model. The fingerprints or the bits, or the 2048 bits that we are going to utilize here, they are going to serve as the baseline for all the models. Okay. Similarly, the gradient boosting also works. It creates trees sequentially to identify the bit patterns or the fingerprints that you provided from your smiles data, and then it will assign something like the weights, and also it can identify the molecular patterns from your fingerprints or from your smiles. We have this multi-layer perception where you feed all these 2048 features hidden, and you might have known from all of the algorithms from the neural network models that it has hidden layers and one output layer, one is the input layer. So our input layer is 2048 features, and hidden layers are divided into different types of neurons, where it can understand, it can extract the data from the input data, and it will feed into different hidden layers, layer 1, layer 2, layer 3, something like that, and then the final output will be your property that you are going to estimate. Okay, these are multi-layer. And deep neural network also works similar to the multi-layer perception, but it has a dense network, so it can learn from different patterns. Okay, so it will learn from the 512, which is your dense or the layer 1. It will learn from that. Then 256 dense layer 2, it will learn from the dense layer 1. And similarly, it will learn from each of the layers, and finally it will give you an output predictions. Okay, these are some of the algorithms. And what are the models that we are going to compare? Linear regression, very fast. Okay, random forest is also very fast. XGBoost and LightGBM a little bit slower than linear models. Deep neural network and the CNN models, they are very, very slow. But I have optimized my code in such a way that you can run it very, very fast, and you can see from the outputs that how much time it takes. So let me show you how much time it takes for the outputs. For instance, these are some of the linear models, and you can see that 1.5 second, and these are the R square, right? That's your prediction value. Time is 1.5 seconds, 0.3, and this is for 27,000 rows, right? So the big model. So anything above 10,000 will definitely take time, but I have optimized in such a way that it can be very, very fast. You can see the Lasso takes around 17.4 seconds, 10.8. This is for one property, molecular weight. So similarly, we have for hydrogen bond donors. Okay, similarly we have for hydrogen bond acceptors, and you can see for LogP, and you have our the TPSA. Okay, and after successful models, so 90 out of 90, so we predicted for 5 into 18 different types of models, so that is that comes around 90. Nothing has failed, thankfully. And you can see these are the R-square values, that how well your data correlates, how well it predicts. So you can see that for the molecular weight, the TabNet performs really well, which is around 0.7. Hydrogen bond donors, acceptors, you can see 0.9, 0.9, and TabNet and multi-layer perception has worked really well. LogP fast neural network has worked really well, which is around 0.9. 90% of the data has been predicted correctly, and this is your multi-layer perception. And you can also look into the time it took and your R-square values, and these are some of the overall statistics, which is around 70% of the test datasets has been performed really well with the prediction values. And once you get those results out of this, so then you can you utilize this code to look into the model performance summary. So how well it is performed, and what is the R-square values, and how much time it takes, and for each of the target properties, not only for molecular weight but also for all the 5 properties that we have calculated. And also you can visualize some of the comprehensive model results out of that. Okay, and you can finally save the models as well. You can save all the models, and so that if you want to predict something out of that, then you can utilize that particular model, the best model that you can take into account, and then you can predict. So yeah, let me show you one of the test examples that I have done. So I have feed all these smiles as a test smiles or test example, and I have utilized some of the models, and you can see that I have utilized all the models in fact, and you can see that how well it is predicting. So this is your decision tree prediction, this is your TPSA TabNet predictions, this is molecular weight with XGBoost predictions, etc. So you can compare the original value or the LogP value of those particular smiles, and then you can compare all of them all together. Okay, and also I'm going to show you, yeah, this is how you can look into the data, how you can predict all the properties. And once you predict the properties, then you need to identify the bit patterns, you know, the fingerprints that I have shown you. So what are the fingerprint patterns that have been used widely in predicting all these properties? So this is a random forest, and you can see that 444, 695, 397, these are the bit numbers or the molecular patterns that I explained. So these patterns have been used in predicting the properties using the machine learning models. Okay, and you can have a clear chart or a visualization graph out of this, so that you can see that what are the fingerprints has been used in predicting all those properties, right? So for instance, in CCO, okay, smiles that you input here, you can see that what are the fingerprint patterns that has been used, like 80, 222, 294, 807, 1057 and 1410, and whether they have the presence or not, you know, the way that fingerprints were fed into the machine learning models, and then it predict all the properties. Okay, so yeah, this is it. I will provide the code in my Omixium GitHub channel and Omixium YouTube channel, and I will create a folder called machine learning on QSAR data, and then I can provide all the codes so that you can run it for your calculations. And remember, let me show you some of the outputs. So it will all the saved models that you see here will be saved as .pkl, and you can utilize all these pkl files to predict some properties for the new molecules, and these are some of the graphs that have been saved. And also there are The CatBoost algorithm that I mentioned, that also has a separate folder where it predicts all the properties and also gives you output that how the training has been performed. Okay, let me also show you something which is the CatBoost algorithm. Yeah, the CatBoost algorithm is it's like having a team of 100 molecular experts where each expert learns from the mistakes from the previous experts. So for instance, how CatBoost really works. So your initial prediction, which is the tree 1, has all molecules 150 daltons. So it learns from the tree 1, and in the tree 2 it fixes the tree 1 errors. So if aromatic, then add 30 daltons. So it will run the tree 3 will run from tree 1 and tree 2, and if it has oxygen, then add 16 daltons. So finally it sums it up and it will give you the final results, which is around 196 daltons. So it is a reinforcement learning from the first input to the final input. So it will learn from the mistakes and it will predict the final output based on the algorithms. This is a really good algorithm if you have regression data, and I think you can also utilize it for the classification data. I'm not sure about that, but you can check about the CatBoost algorithm. It's a very fast algorithm, and we can also look into the CatBoost algorithm, how well it performed. Let me see whether I can find it or not. Let's see with yeah, the boosting algorithm. The boosting algorithm, yeah, the CatBoost boosting algorithm, it the training time is really fast, and you can see that R square is around 0.9, which is also a good model. So you can utilize the CatBoost model for your QSAR data as well. Okay, and remember that your data has to be your data should contain all these properties in order to predict all these 5 properties. So this particular data, you can modify your data set as you like, but the main thing that you require is your zinc IDs, your smiles, LogP values. If you want to predict LogD, that also you can predict by utilizing this model, molecular weight and all those stuff. So this is the molecular descriptor data that you can utilize to feed into your machine learning models. Then you can predict the properties for your new molecules. The more number of data means the more accurate will be the model. So in my case, 27,000 works pretty well, but you can feed. I have also done the similar kind of machine learning model for almost like 1 million compounds, and it really works pretty well for predicting new compounds properties. Okay, thank you very much.